KMP solve substring search. Given a text and a pattern, we want every starting index where the pattern appears. A naive search can repeat work. At start 1, it first matches AB. Then the match fails, the pattern expects C, but the text has A. KMP does not throw away everything after that mismatch. It uses the pattern's prefix information to know how much of the match can still be reused. That prefix table is called the LPS array. It lets the search move the pattern pointer back, without moving the text pointer backward. In this example, the pattern appears at starts 5 and 10. LPS stands for longest proper prefix, which is also a suffix. Proper means the prefix cannot be the whole string. Look at ABAB. The prefix AB and the suffix AB are the same, so the LPS value is 2. This value tells KMP how far the pattern pointer can fall back after a mismatch. We keep the reusable AB match. For the full pattern, the LPS array stores this fallback information at every pattern position. Now build the LPS array for the given pattern. LPS at each cell means the longest proper prefix of the substring ending there, which is also a suffix. The key comparison is always pattern at I against pattern at length. Cell 0 has only one character. A one-character string has no proper prefix, so LPS at 0 is 0. For cell 1, compare pattern at I with pattern at length. They do not match, so LPS at 1 is 0. For cell 2, compare pattern at I with pattern at length. They match, so length becomes 1, and LPS at 2 is 1. For cell 3, compare pattern at I with pattern at length. They match again, so length becomes 2, and LPS at 3 is 2. For cell 4, compare pattern at I with pattern at length. They do not match, so we fall back and try a shorter reusable prefix. Why does fallback use LPS of length -1? Because the part already matched may contain a smaller prefix that is also its suffix. In the small pattern AABAAC, at I equals 5, length is 2. The comparison fails, but LPS at 1 is 1, so we fall back to length 1 and try again. For cell 5, compare pattern at I with pattern at length. They match, so length becomes 1, and LPS at 5 is 1. For cell 6, compare pattern at I with pattern at length. They match, so length becomes 2, and LPS at 6 is 2. For cell 7, compare pattern at I with pattern at length. They match, so length becomes 3, and LPS at 7 is 3. For cell 8, compare pattern at I with pattern at length. They match, so length becomes 4, and LPS at 8 is 4. The completed LPS array is 0, 0, 1, 2, 0, 1, 2, 3, 4. Now use the LPS array to search the text. The search compares text at I with pattern at J. On a match, both pointers move forward. At the beginning, text at I is B and pattern at J is A. Since J is 0, there is no fallback, so only I moves forward. Starting at text index 1, for characters match. Then text has a while the pattern expects C, so KMP does not move I backward. Instead, J falls back using LPS at J-1. Here J goes from 4 to 2, and we compare the same text character again. The scan continues from there. When J reaches the pattern length, we found a match ending at the current text position, so the start is I minus pattern length. After a full match, J falls back again instead of restarting from 0. That reused suffix lets the next match at start 10 finish quickly. The search reports matches at starts 5 and 10. Why is the fallback safe? Look at this mismatch. We have already matched 4 pattern characters, but the next comparison fails. The matched part is ABAB. Its suffix AB is also the pattern's prefix AB. That is exactly what LPS at 3 equals 2 means. So KMP shifts the pattern until that prefix AB sits on top of the already matched suffix AB. The text pointer does not move backward. The skipped alignment cannot be a match. It would start on AB while the pattern starts with A, so checking it is wasted work. This is the reason KMP is linear. Every fallback preserves a possible match, skips impossible alignments, and keeps I moving forward. KMP runs in O of n plus m time. Building LPS scans the pattern once, and searching scans the text once because I never moves backward. The extra space is O of m for the LPS array. Define a helper that builds the LPS array for the pattern. Start with an array of zeros, 1 slot per pattern character. Length stores the current reusable prefix length. Begin scanning from index 1 because LPS at 0 is always 0. Keep processing until every pattern index is filled. Compare pattern at I with pattern at length. On a match, extend the reusable prefix length. Store that length into the current LPS cell. Move to the next pattern index. If there is a mismatch but length is not 0, fallback. Fallback means try the next smaller reusable prefix. If length is already 0, no prefix can be reused. Store 0 for this cell. Then move forward. Return the completed LPS array. Define the main KMP search routine. First build the LPS array from the pattern. Create a list to store match starting indices. Start both pointers at 0. Scan while the text pointer is still inside the text. Compare text at I with pattern at J. On a match, advance both pointers. If J reached the pattern length, a full match was found. Add the start index, I-m, to the answer. Then fallback J using LPS so overlapping matches are not missed. If there is a mismatch and J is not 0, fallback J. This keeps I at the same text character and tries a shorter prefix. If J is 0, no prefix can be reused. So advance only the text pointer. Return all match starts.